Last time, we introduced this angular momentum operator, r cross gradient times h bar over I. We would like to represent such an angular momentum operator and vector in the spherical coordinate. So this is the, this cartoon picture of this spherical coordinate r theta and phi, which defines any position in three-dimensional space in terms of the spherical variables. Unit vector r pointing to the radius direction, and theta is the direction from the theta direction, right? So this is theta. And phi is the angle in the xy plane. So these three unit vectors form orthogonal basis, which is the equivalent, say, coordinate system to the xyz coordinate, Cartesian coordinate. And there is a transformation between this xyz, r theta phi. And this is part of this transformation that link between the theta phi and xyz. And you simply just plug in this gradient operator. Okay, so this is the definition of the gradient in the spherical coordinates, which you can find in any applied maths textbooks. So simply just plug in, and across by this vector r, you'll find that this is the expression of the angular momentum operator in the spherical coordinate, which indeed is a function only theta and phi. So any dependence on this radius or this radius vector is gone. This operator depends only on theta and phi, and also d by d theta and d by d phi. And that justifies why we call this angular momentum operator, because this depends on this angular variables. But we could still make context of this representation of the angular momentum operator with the Cartesian representation of the operator, namely this Lx, Ly, and Lz. With the help of this transformation, taking this between the spherical variables and Cartesian variables. If you plug in this transformation, coordinate transformation, so you will find this Lx, Ly, and Lz expressed in terms of the theta and phi. This is a very convenient expression that we will use that expression later, right? Based on this coordinate transformation, we are able to construct this L plus and L minus operator. Simply just take the linear combination Lx plus minus ILy, and where this Lx and Ly are given by this angular dependence. So let's just do the algebra. So it's very easy to do, and when you finish this summation and subtraction, you'll get very simple form. L plus and L minus, which is simply just plus minus h bar times e to the I phi, and times this derivative of the angular variables, d by d theta and d by d phi. Again, do not simply just memorize this, because you need to derive this, okay, by yourself. So the way that you derive this is, again, by this coordinate transformation, and you could also derive such a coordinate transformation by yourself, and then you could derive this, derive everything. We will take advantage of such angular dependence of this angular momentum operator, try to construct this eigenstates, simultaneous eigenstates Ln, remember Ln, which is the simultaneous eigenstate of L squared, Lz, the Hamiltonian. But we know that this is more convenient if we express everything in terms of spherical coordinates. So that's what we'll do. We try to represent this Ln simultaneous eigenstate in spherical coordinates, because this is what we should do. By symmetry consideration, this is the thing that we must do, because when the system obeys certain symmetry, we could, we must use, the variables or coordinates that respect such symmetry. The symmetry in this problem is the spherical symmetry. Remember, the potential term shows a spherical symmetry, meaning it depends only on the magnitude of the radius vector. and nothing else. As a result, the Hamiltonian respects such a spherical symmetry. As a result, the best or the only coordinate that we should represent everything is the spherical coordinate, which again is the consequence of the spherical symmetry. And we will define such a eigenfunction by YLM, which we call the spherical harmonics, which is the projection of YLM state onto this spherical coordinates. So in other words, this is a Schrödinger type of wave function, but not in the Cartesian coordinate. Instead, is written in terms of spherical variables. So now you should be very familiar with this kind of a projection or a realization of a Dirac state in any, say, orthogonal normalized spaces. In this case, we choose theta phi as our normalized coordinates. The way that we do this is again by the kind of a unit operator that we already proved and used many times in the past. Namely, we could simply expand this unit operator in terms of any arbitrary normalized coordinates, but here we choose this normalized spaces to be the spherical basis. Namely, suppose we have this eigenstates or eigenbases formed by this theta and phi, we could consider this kind of a part of the sphere that is projected onto this xyz axis. We could integrate over the solid angle that is formed by this vector r. After we integrate over this solid angle, which I'll define in just a moment, and we could show that this is, again, we demand that this will be our unit operator. Okay, so what is the, say, solid angle? So this is the volume enclosed by this vector r in three-dimensional space. Imagine that this is part of the sphere, all right? So this small volume of a big sphere is actually enclosing this vector r, and the endpoint of the vector r is actually on the surface of such a small solid angle, the omega. So you could very easily work out this projection of this three-dimensional vector r in the spherical coordinates. And this is, so let me just write it down right here. So this is theta, and this is phi, and this is r and theta. Okay, so you can very easily calculate the length of this projection. For example, this is r sine theta. This will be r cosine theta. This will be r sine theta cosine phi. So the solid angle is defined by this volume enclosed by the orange curves, and also bounded by this xyz axis. So we need to integrate out this kind of matrix formed by this theta phi eigenspaces over the entire the omega, or the solid angle. How do we do this integration over a solid angle? Well, you have learned this in your applied math, I believe. So you need to separate this integration over the solid angle into two parts. One is the integration over phi, another is over theta, and theta runs from 0, which is this a positive z-axis, until pi, which is the negative axis, z-axis, and the phi is actually the angle in the xy plane, starting at 0, enclose a complete circle. You integrate over phi from 0 to 2 pi. Of course, you need to multiply this by a sine theta, which is simply this volume this orange volume and over a unit sphere. This is what you can do. And we will show in just a moment that how do you define such a projection of a two normalized eigenbases theta phi and theta prime phi prime. Of course, this is proportional to this delta function. So this is delta theta minus theta prime, delta phi minus phi prime. However, there is a prefactor. And this prefactor is precisely 1 over sine theta, which comes from this solid angle integration. We'll see that in just a moment. All of this algebra come from your applied math and coordinate transformations between Cartesian and spherical systems. Okay, so let's take a short break. This is a straightforward calculation. I believe that all of you have learned such coordinate transformations, especially the solid angle, integration over solid angle, that kind of. The main goal of this kind of mathematical manipulation is to find the Schrödinger wave functions or eigenfunctions of angular momentum operator. As I mentioned, since the system shows a spherical symmetry, as a result, it is natural to represent everything in terms of the spherical variables. We should construct, based on this L plus, L minus, in the spherical variables, eigenstates of L squared and Lz, and this is the thing that we need to figure out. And this is also the basis of solving the Schrödinger equation for hydrogen atom in the next chapter, because you'll see later that YLM, spherical harmonics, constitutes a very important part of the Schrödinger wave function or eigenfunction of the hydrogen Hamiltonian. We will come to this very soon. Okay, so let's just derive this prefactor 1 over sine theta from this normalized condition in this spherical eigenbasis theta and phi. So the way that we show this is again by plugging this unit operator right here on the right of this Dirac-Broglie state theta prime phi prime. What you know is that this unit operator 1 is kind of a transparent. You could simply just forget about this, or you could just use this expansion theorem to represent such unit operator in terms of this spherical eigenbasis theta and phi and over the solid angle the omega. Okay, so you could either just throw this away or use this expansion theorem. So that's the magic. So if you simply just don't look at this unit operator, this is nothing but, again, theta prime phi prime. But if you look at this expansion expression, we know that at the end of the day, this kind of a solid angle integration should actually lead to the theta prime phi prime, which is to say that this, the whole thing, this solid angle integral should actually reproduce this theta prime phi prime, which means that this whole thing is actually equal to this kind of a delta function. Okay, in the integrand, where when you integrate over theta by this delta theta minus theta prime, you should get 1 only when theta equals theta prime. And likewise, if you integrate over the phi by this delta phi minus phi prime, integration reports the result to you as a 1 if theta phi is the same as phi prime, which means that this, the whole thing, this integral over a solid angle of this d theta d phi integration of this theta phi Dirac-Broglie state will lead to Broglie state theta prime phi prime. The only way that you could reproduce such a result is that you should insert the Dirac delta function in this angle integration. But you know that what is this? The omega, well, the omega is nothing but this double angular integrals over d phi and d theta and multiplied by sine of theta. This projection and times Dirac-Broglie state. In other words, you should compare these two. Since these two expressions are identical, you simply just compare this two expressions, you know immediately this final result, okay, where this inner product between these two angular eigenstates, theta phi and theta prime phi prime, when we make such an inner product, the result is given by this product of the two Dirac delta function, theta minus theta prime, phi minus phi prime, and also multiplied by additional normalized factor 1 over sine theta, okay, because this and that should be identical. So you move the sine theta to the other side of the equation and you get 1 over sine theta. So this is the correct normalized condition for theta phi eigenbasis. Of course, in the Cartesian coordinate, say x and x prime, this is simply just delta x minus x prime. But in the spherical coordinate, you get extra factor, which comes from this integration over a solid angle. Good, so we will take advantage of such a normalized eigenbasis in the spherical variables, like this one, for later purposes. Let us just rewrite this angular momentum operator Lz and also L plus minus one more time. And so if you just plug in the definition of this Lz, which is xpy minus ypx, and plug in this coordinate transformations between the Cartesian and the spherical variables, then you'll see that this is nothing but very simple operator, which is h bar over I times d phi d phi, right? So we have proved that. L plus L minus is this one. We will use these relations and equations to construct this y or m. Let's just define this formally, this y or m from the expansion theorem. As before, any arbitrary Dirac state could be expanded in terms of any complete set of eigenbases, and here we choose this eigenbasis to be this theta phi state, which is the eigenstate of a spherical coordinate. You could sum over all possible quantum numbers L and m, and since we already derive what they are, runs from minus L to plus L, and L starts from 0 to infinity. Suppose that this is just orbital angular momentum. L takes the integer value. The coefficient of this expansion is called CLM, and by the normalized and orthogonal condition of Lm states, you get this coordinate delta function. So once you make an inner product between these two, say angular momentum eigenstate Lm and L prime m prime, what you get is simply just Kronecker delta function. So this tells us that when L is the same as L prime, you get 1, and equals m prime, you get 1, otherwise you get 0. You immediately get this coefficient CLM, which is simply just a projection of your Dirac state psi onto this Ln eigenbasis, right? So this is application of what we learned previously regarding the expansion theorem of Fourier expansion theorem. So now you could just rewrite everything. The Dirac state psi is given by this double summation, right? And you know very well that this completeness of this Lm eigenstates, when you sum over all possible L and m of this matrix formed by Lm cat state, Lm bra state, so you get back to this unit operator. You simply just use that kind of a unit operator, expand it in terms of this Lm eigenstate, you'll get this. In other words, we could actually construct such an inner product between theta phi and theta prime phi prime in terms of the complete set of eigenstates Lm, which is the eigenstate of L squared and Lz. But what is this? This is on the right hand side of the equation. This is precisely what we obtained already, which is 1 over sine theta Dirac delta function, theta minus theta prime, times delta phi minus phi prime. So this is precisely what we had just over there. But what is this equation on the left-hand side? Well, on the left-hand side, this is what we already defined, the YLM spherical harmonics. So this is YLM as a function of theta and phi. This is YLM star. Remember, this is the conjugate part of this YLM because, on the left-hand side of this matrix element, Ln is on the right side, and theta and phi appear on the left side. Okay, but on this, the right yellow circle, you get, the opposite arrangement of Ln and theta and phi. On the right, you get YLM. On the left, you get YLM star. As a result, if you look at these two sides of the equation, you get the normalization condition for YLM, which is sum over Ln YLM star theta phi prime times YLM theta phi, which is 1 over psi theta delta. Okay, so this is the orthogonal and normalization condition for spherical harmonics, which we will use later. Okay, so this normalization condition comes from this one. We simply just represent such an identity in terms of Ln eigenstate. Once we expand this identity in terms of the Lm eigenbasis, we got YLM naturally. Our step is to show that to actually work out this YLN. So what is YLN? We don't know what that is at this point, but we will calculate YLN by solving this eigenvalue equation for angular momentum operator in the spherical coordinates. Let's take a short break. 这里就是很简单的一些数学就是用坐标转换的关系式这个 Spherical Harmonics 可能是各位比较陌生的一个函数现在开始需要熟悉它那它未来扮演非常重要的角色，在解氢原子的薛定谔方程式的这个计算上面，我们需要 Spherical Harmonics 的帮助。Let's try to solve this YLN. As I mentioned, we need to take advantage of this raising and lowering operator L plus and L minus when we try to construct all these eigenstates, plot these energy levels one more time. So it actually come from the lowest level, where m equals minus L, to the top level, which is m equals to plus L. So there are 2L plus 1 states. You could either start from this lowest level, the ground floor, take the elevator to the top floor, and this elevator that takes you from the ground floor to the top floor is actually L plus. Remember that. You can also take the elevator starting from this top floor one by one, and this elevator is actually L minus operator. Either way is fine. So there are two steps that we could, in fact, there's 3 steps. So first, we need to identify either the top floor eigenfunctions or the ground state, the lowest level wave functions, eigenfunctions. So before that, let me just remind you that we have these two expressions of L squared and L plus L minus product in terms of theta and phi, which can be used for later. But before we figure out this eigenfunctions of the top floor or the bottom floor, let us just do the simple algebra observation that suppose I apply this Lz onto any eigenstate Ln. I take the inner product of that resulting state with the theta phi eigen coordinate, then what I get. Okay, so because we know that Lz operator is simply just h power of I d by d phi, right? Suppose I know this eigenfunctions already. If I apply the Lz operator equivalently what I need to do is take the differentiation of that wave function with respect to phi and multiply by h bar over I. So let's just see this, what this will help us to solve for this y or m, in particular the phi dependence. So we can sort of guess that this y or m could be separated in terms of the product of the two type of functions. One is the function phi, capital Phi, which is a function of only phi, and another is called f function, capital F, which is the function of theta only. So this is our educated guess, because we know that this, when I apply the LZ operator, what I get is nothing but differentiation of that wave function back to phi. It sort of tells us that you can solve this differential equation separately. Okay, and this is indeed the case. If I apply this eigenvalue equation for LZ, acting on this Lm, I get mh bar. So this is, by definition, eigenvalue equation, because Lm is the eigenstate of Lz with the eigenvalue mh bar. And this follows the eigenvalue equation, but at the same time, from this spherical representation of the z operator, I know that this is the same as taking differentiation of this eigenfunctions back to phi and multiply by h bar over I, because I could define this differentiation in terms of this kind of a standard way that we get this derivative, which is the subtraction between these two wave functions, slightly different angle phi. Here is phi plus delta phi, and on the right side this is phi, and divided by this small angle, take the limit of when delta phi equals 0, multiply by h bar over I. So this is precisely the definition of this, taking the differentiation of this wave functions back to phi. And so I can simply just link these two. This is coming from this eigenvalue equation of Lm state, and on the very last line, this is nothing but the operator representation of Lz in the spherical coordinate. So these two should be identical. So let's just equate these two parts of the equation, which tells us immediately that if I take this differentiation of Lm with respect to phi, I get I times m times the same thing, which you can simply just look at this equation. So this is partial Lm, partial phi, and you actually move this h bar over I to the other side of the equation, get rid of this h bar, and this is precisely what you get. I times m times this same function. So this is Ylm, and this is Ylm. In other words, you get a very simple differential equation, partial Ylm, partial phi, which is I times m times Ylm. So this simple equation tells us that Ylm could be actually decomposed in terms of the two different functions. One is the function of only phi, because you can solve this pretty easily. So the solution of this differential equation is given by e to the im phi times another function which is independent of phi, and which again a function of theta. And this actually proves our earlier educated guess that Ylm could be decomposed in terms of the product of two functions. One is a function of theta only, another is a function of phi only. So now we solved part of the problem already, which means that this Ylm shows a factor of e to the im phi multiplied by a unknown function, which I call this f function, as function of theta. And in this f function, there's no phi dependence here, because all the phi dependence already here, e to the im phi. Because this is the only equation that links to this phi dependence of Ylm. And we solved that already. So now let's just look at this f function. So how do we get the solution of f function? We'll need the help of the ladder, okay, the elevator. The next step is that suppose I'm on top floor which is the maximum value of the m, which is plus L, which means that LL state. If I'm at LL state, I cannot go even higher floor because there's no floor available. So this operation simply vanishes. Likewise, I could go from the very bottom floor, but you could do that either way. Suppose I'm on top floor and I want to go even higher floor, which is not possible because when I apply L plus on LL state, I got 0. Plus acting on LL state vanishes, which is precisely what I wrote here. So 0 equal to this kind of operation. I could actually project or take the inner product of that state and theta phi state to actually extract this eigenfunctions or Schrödinger wave functions in the spherical coordinates. When I do so, I get what? I get this definition of this L plus acting on the theta phi state, which is this operator. I wrote it down somewhere previously. Okay, so you simply just copy what we derive for L plus and plug in here. The remaining part is nothing but YLL, because now m equals to L, which means that you need to take this operator and onto the YLL state or function, and this operation will vanish. Okay, so this is the condition that you get this top floor wave function YLL as a function of theta and phi. You simply just collect all this differentiation because we know that this YLL is what? It's FLL, it's a function of theta times e to the I n phi, whereas n in this case is equal to L. So you plug in what we derived in the previous step and insert it here and take the differentiation of this YLL functions back to theta and phi, and this is what you get. You get the differentiation or differential equation for FLL function as function of theta, and that differential equation should become 0 because this is what you start with. If I could simplify this differential equation, and this is the equation that we need to solve. d by d theta minus L times cotangent theta, everything multiply FLL, function of theta vanishes. And this is also a very easy differential equation to be solved, and the solution of FLL theta is given by sine theta to the power of L. So if you plug in this solution, actually satisfy this differential equation. So now we have almost everything we need to know, except we simply just know the eigenfunctions of the top floor state. On top floor, the eigenfunction is YLL, which is given by what? E to the I L phi times FLL. And we know what FLL is, so this is given by e to the I L phi sine theta power of L. So we will check this normalization factor later, right? Suppose this is the eigenfunction of the top floor eigenstate. I know everything on the top floor, so I can actually take the elevator down, right? Go downstairs one by one. Now, if I take the elevator once, I go to this L minus 1 floor, and then I can actually go further down until I hit the bottom. So what is L minus operator? Let's just do it. So the general eigenstate Lm could be reached by applying this L minus operator repeatedly. In other words, this YLM in general as function of theta and phi It's actually the normalization factor C times this L minus operator to the power of L minus m e to the I L phi. This is your YLL, and you simply just apply this lowering operator L minus onto this top floor wave function, so you get any arbitrary eigenfunction that you want to go. So suppose this is a function n, this eigenstate n. When you go from the top floor and you want to end at this state n, how many L minus operator that you need to apply? Of course, this is the answer. You must apply L minus to the power of L minus n. So simply just do the counting. Now from the top floor to the next lower level, you get L minus operator. So once and twice, and when you reach this n floor, now you must apply L minus operator to the power of L minus 1, which means that you should apply L minus operator L minus m times. And this is precisely what you should do. So, but what is L minus? Well, L minus is easy. So you simply just spell it out. The definition of L minus is this operator. In other words, you only need to do this algebra by applying this operator L minus m times onto this eigenfunctions on the top floor and multiplied by this normalization factor C. So the C could be derived from the normalization condition. I think this is the most important lesson that we learned today. So the operator method in this special case of angular momentum operator tells us that we need to find out at least the eigenfunction, the wave function of the top floor eigenstate, or the bottom level eigenfunction. So once we know either top floor or the bottom floor eigenfunctions, then we can take the elevator to any floor we like. In other words, this kind of taking the elevator is the essence of this operator method in quantum mechanics. So you really need to understand and need to know how you take the elevator. What is your elevator? Therefore, the key word for this chapter and also all the remaining chapters in quantum mechanics is define your elevator. Find out the eigenfunction of either the top or the ground floor. So this is a very important message. The remaining algebra is a straightforward mathematics. You don't even think about memorizing this. Don't even memorize this. But this is what you need to learn. You need to know what your elevators are and what your elevators in terms of the convenient variables, for example, x, y, z, or theta and phi. And the next is to find out at least a complete solutions of one of these eigenstates. This could be either the ground floor, ground state, or the top floor eigenfunctions. And then you need to go to any floor by taking the elevator. Taking the elevator is the most important job that you need to learn. For example, in the final exam, I could simply just ask you to do the job. Suppose I have just 3 eigenstates labeled by, say, n equals to 1 and 0 and minus 1, for example. In this case, L is actually 1. Okay? Suppose one of these eigenfunctions, say the lower level, the ground floor, you are asked to take the elevator to the top floor. Okay, suppose you know this y1 minus 1. I'm asking you to find out what this Y11 is. In that simple exercise, you need to really derive first the eigenfunction of the lowest ground floor, and then learn how to take the elevator. And therefore, you don't need to memorize anything. You just need to define your elevator and take the elevator. That's all. This is the power and magic of quantum mechanics, in particular regarding the operator method. So this is the essence of operator method, that you could take advantage of such an elevator, which are in the form of the, say, operator. What this operators will do is just take some differentiation of this wave function with respect to theta, phi, or x, or y, or z, and then you repeatedly just take this elevator to any floor you want to be. So you must learn this. Okay, the remaining text is nothing but algebra, some differential equation. Taking this derivative, these things are really trivial, or at least straightforward, but the main idea you must capture and learn in this course. So let me emphasize one more time, don't even think about memorizing this. It's totally forbidden. But you really need to derive everything. The way that you derive everything is, again, by taking the elevator. So you must learn how to construct your elevator in terms of quantum mechanical operator, and how to find this one of the eigenfunctions, and then just take the elevator. That's all. I'm repeating myself, but this is worthwhile repeating, that memorizing this is really a stupid thing that you could do. The smart thing to learn quantum mechanics is to construct your eigenstate all by yourself. So this is the most important message I want to convey today. When you learn physics, you should learn the spirit and the essence. Taking the elevator is the essence, it's the key right here. All this complicated function of theta and phi, that's just, you could figure that out pretty easily. Let's just make a final comment and remark regarding this YLN, spherical harmonics, and their links to the so-called Legendre polynomials. 相信大家都应该明白了哈，这部分的重点是放在利用 raising lowering operator， 然后你可以到达任何一个 eigenstate。这些 arbitrary 的 eigenstate 的 wave function 是需要各位可以去导出来的，并不是去死背硬记的哈。那所以我这边严格的不能说禁止，你要背就是你的事，但是这绝对不会是学习量子力学的好方法哈。那最好的方法就是我刚刚提到的，就是用这个升降梯的概念哈。这个 elevator 这个概念在量子力学的很多其他的这个系统里面都会一再的反复的出现。因此呢，有关于这个用运算符的，还有这个狄拉克的表示这种符号这样子的一种运算呢，是各位必须要熟悉的，而且必须要在这门课学会的。在已经快学期末了哈，所以这部分未来各位在更高阶的量子力学的课里面会一再的出现。even 你未来不走这个理论哈，量子力学这个方面，你在其他的应用的学科哈，比如说半导体、光学、雷射哈等等哈，任何的跟量子科技相关的学习的科目里面，你都会需要用到这个量子力学这个能阶这个概念哈。以及你怎么样能够到达那个能阶，好，那能阶跟能阶之间的跳跃呢，会产生一些 energy 哈，释放出来。那这些量子的概念呢，我们在这门课里面会强调它的这个运算符号的计算这部分。所以我刚刚举了这个例子呢，也就是这些课本的习题里面提到的这些简单的计算哈，是假设我知道了某些简单的 energy level 一些它的本征态的本征函数的话，那你需要会 到达其他的 eigenstate 的方法。Let's just make a final remark regarding the spherical harmonics while n. So you could just do this elevator thing, taking you to any eigenstates. In general, this while n is given by this function right here. So you can see that this e to the I phi is here. F function that we just mentioned is this FLN as function of theta, in particular as function of a cosine theta. And this prefactor is just a normalization factor. PLN as function of cosine theta is what we call this special function called Legendre polynomial, which is defined in this form right here, which is the derivative of this 1 minus u squared to the power of L by L minus m times, where u is cosine theta. And this P minus ML is related to PML by this prefactor. Anyway, you could solve this differential equation formally. Maybe we could just make one more remark to derive this PLN, this Legendre polynomial. You could expand this Legendre polynomial depending on m and L. For example, when L is 0, m is 0, this P0 is nothing but 1, and this P1 is actually x is actually cosine theta. And P2 is this, and P3, and so on and so forth. So you could really do the algebra by taking this L minus m times and multiply by this factor. And this is what is the Legendre polynomial telling you. And applying the Legendre polynomial back here, you actually get all this while n. For example, this y00 is just a constant, and y11 is given by the sine theta times e to the I phi times prefactor, and so on and so forth. So suppose you know this y11. Suppose y11 is given, you should know how to get the other yn. Say 110, y1 minus 1. So in other words, you don't even bother memorizing this because this will be given. But once this is given, this is your job to actually derive all the others. Sounds straightforward, simple, and so on. In general, you could look at this kind of a probability distribution of this while n. Suppose n is at the minimum value plus minus L, which again is proportional to sine theta to the power of 2L. In this case, you could just make a plot of this, the square of YLL. Okay, so if you plot the square of the YLL in this three-dimensional spherical coordinates, you will find that this is the probability distribution of your eigenfunction, right? But this distribution is highly confined around the equator. The equator is here, theta equals to pi over 2, which is indicated by this red circle right here, because when this is maximum, sine theta is actually 1, which means that theta is actually half a pi. Around the equator, you get this largest probability. In that case, this is very close to the classical angular momentum vector. So in the classical angular momentum, when L is very close to LZ, and you get this type of angular momentum. So suppose there is a rigid body and circling around this xy plane. In that case, you get only the z component of the angular momentum vector. Suppose the rigid body is moving around in the xy plane. Likewise, in this quantum mechanics, it looks like all this probability distribution is centered around this equator, which means that this quantum particle may be easily found near the equator of the sphere. But of course, this is not an exact statement because you should have both Lx and Ly component in quantum mechanics case. But we could write down such an approximation. Suppose in quantum mechanics, I want to know the deviation of del z from this total angular momentum L squared, what I get is this L plus times L plus 1 minus L squared divided by L times L plus 1. So suppose I subtract this L squared by Lz squared and divide it by L squared. I simply just take the eigenvalue of this numerator and denominator. So in the numerator, I get L plus 1 minus L squared. In the denominator, it's L plus 1. So I simply just get 1 over L plus 1, which approach 0, suppose L goes to infinity. In other words, if the angular momentum quantum number L goes to infinity, most of the component of angular momentum lies along the Lz component, which tells us that this quantum particle is mostly circling around this equator, which looks like this classical limit. However, this doesn't tell us there's no Lx and Ly component. This is a very important point. Suppose Lx, Ly, and Lz both vanishes. If this is the case, then we have a trouble because this commutation relation is violated. In the extreme classical limits, you may think that while there is no xy component of angular momentum operator or components, but this is wrong because suppose both Lx and the y components are 0, then by definition, if you want to satisfy these commutation relations between Lx and Ly, which is given by h bar Lz, which means that Lz must vanish as well. But Lz is not 0. So in order to satisfy these commutation relations, you cannot simply just assume that both Lx and y components are 0. The more realistic picture of this angular momentum vector in quantum mechanics is this. You have the largest component pointing to the z direction, but still you have finite components of the angular momentum vector pointing in this x and y. So in other words, you don't have 0 Lx nor Ly, but both Lx and Ly should keep finite in order to satisfy this commutation relation. So, but the most components, or the majority of this angular momentum vector in quantum mechanics in this classical limit should correspond to this equator or the Lz component. As a result, there is a subtlety here when we compare the classical limits of this quantum mechanical angular momentum operator. So the subtlety is the uncertainty relation, also this kind of a commutation relations between angular momentum components. That's almost all you need to know. There's one more thing that we could derive, which is a formal derivation of this YLM. It's a more mathematical approach, which we could do it in just a moment. Okay, so let's take a short break. 看大家都很明白这个量子力学的运算，关于角动量的运算符这个部分，spin。所以这也是量子力学导论，就是说这个一学期的课大家需要会到的部分。接下来第10章以后呢，就是可能是比较进阶版的量子力学。各位有兴趣的话，可以旁听或者修研究所的量子力学这门课。不过我相信，如果就是说是在固态物理的这些基础的这些科目呢，大概到病这个部分也差不多可以够用了Let's just formally derive this YLM by solving this eigenvalue equation for L squared. This is the eigenvalue equation for L squared. I simply just project this Ln onto the theta phi eigenbasis. On the right side of the equation, this is nothing but YLn theta phi. But then on the left side, I simply just plug in this L squared operator in terms of theta and phi. So we already derived this L squared. So then you simply just relate this two sides of the equation, and this is the differential equation for YLM. As I mentioned, we take the educated guess by assuming that the YLM is simply just a product of the two different functions. Capital theta as function of theta times capital phi as function of phi. So just plugging these answers back to the differential equation, you get this line right here, and also this type of equation for phi. This is for theta and this is for phi. So we solve this capital phi part of the YLM first, and the solution is simply just e to the im phi. But we know that phi represents the azimuthal angle around this xy plane. This angle right here circling around this xy plane, the xy axis, and when you go back to the starting point, this phi is changed by 2 pi. But you know that when you go back to the same angle phi, this wave function should actually be the same. Therefore, you get a periodic bounding condition that this capital phi, when you actually move this phi by, change this phi by 2 pi, and this function actually the same. It's the same as before. But this immediately tells you there's a quantization for this, this m, because e to the 2im equals to 1. Why is that? Because you simply just plug in this solution, e to the im phi is the same as e to the im phi plus 2 pi, or minus. Okay, as a result, this is e to the im phi, e to the im 2 pi, which immediately tells you that m can only be integer, 0, plus, minus 1, and so on and so forth. Good, and this is precisely what we found earlier, right? So n is actually from minus L to plus L, where L, in the case of the orbital angular momentum, is the integer. And here, we don't know about the physics. What we know is just solving for the eigenvalue equation for L squared. And you could actually plug in this solution back to this equation for theta, and this is the differential equation for theta as function of theta. And the solution is the Legendre polynomial. This is a well-known special function in mathematical physics. So you simply just look at this textbook special function, and this PLM as function of the cosine theta is defined by taking differentiation of the PL function with respect to x, where x is a cosine theta. And then we actually are done, because this is precisely what I wrote down previously, and this is the formal derivation of this PLM, or Legendre polynomial, also the official derivation for YLM. But the more physical and more intuitive way to derive the same thing is by taking the elevator, as I mentioned many, many times. You could do that either way. Okay, so that concludes everything with this angular momentum operator today. Next time, next Monday, we will start solving the Schrödinger equation for hydrogen atom, which is again a combination of YLM, the radius part of the Schrödinger equation. We will spend some time in solving for the radius part of the Schrödinger equation for hydrogen atom, and then we know everything about YLM. We simply just plug in the YLM when we solve for the hydrogen atom, and that's what we will do. And the radius part of the Schrödinger equation for hydrogen atom is very similar to what we have done earlier when we solve for the harmonic oscillator problem by brute force. We should assume this polynomial. We plug in this polynomial, and we need to truncate that polynomial at a finite number of terms, and then we get a quantization of the energy levels. So that's sort of using the same technique. Okay, so then we will actually figure out these energy levels and quantum numbers for this hydrogen atom, reproduce everything you know and you learned in high school, chemistry and physics, and also general physics. So that's it for today, and I will see you next Monday.